Hello, folks. Can you hear me on the chat? Wonderful. Thank you. Okay. So the semester is winding down. This is the last official class period for the semester. The main goal of today is to go through the last bit of information, that's the new information for this week. That should probably take about 30 minutes at most. After that, I have some muddiest points I'll go over, and then I will open it up to questions from everybody. I'm going to keep the chat window open, so please feel free to send me questions as we're going along, and I'll try to address them. Logistics. So the plan is to try to release the midterm exam number 4 today at 5 p.m. It is not due until the end of finals week, the Friday of finals week. Also due today at 5 p.m. is the small group activity. Immediately following, the quiz for that small group activity should open up, and it will be available until 5 o'clock p.m. tomorrow. The last 2 homeworks are also due tomorrow, homeworks 13 and 14. The 3 portions of the final exam are going to open on Monday morning, and they will be due on Friday at 5. So the midterm 4 and the 3 parts of the final exam will be due at the same time, Friday at 5. All 4 of those elements can be taken independently. The usual 3-hour time frame for the midterm. The final portions are going to be significantly shorter than what you've seen before, and so we're looking at an hour of time for each of those. Any logistical clarifications before we move on to the content? If some come up, please put them in the chat. Otherwise, we will get moving on some of the content. So I'm going to share screen here. We'll share this. Okay, so what we have here, I'm going to do a real brief touching on the topics that we set up on Monday/Tuesday. So we went through redox reactions, understanding them as reactions where you donate electrons or you accept electrons. Or actually both of those are happening in 2 different places, which we are able to identify by looking for changes in oxidation number. We looked at how we can separate the oxidation portion from the reduction portion into 2 half cells that we then connect into an electrochemical cell where the overall reaction is happening split between 2 different places. The electrons flow along the wire, and we can have them do work in between, and we can measure the potential they have with a voltmeter, and we complete the circuit with a salt bridge where the charge flows the other direction in that case. We also represent the notation of cells in this way. This type of notation specifies pretty much everything you need to know about the circuit that you have. We talked about how the voltage that you see is a function of each of the 2 sides combined. We talked about measuring those against the voltages against a standard hydrogen electrode, defining that one to have a voltage of 0. And so then we are able to find half cell potentials for any species we want, which are then tabulated as reduction potentials. Now, if the reaction that you're looking at, the half reaction you're looking at is going in reverse, meaning that it's an oxidation reaction. All you do is you take the opposite, the negative of the potential that's listed here to have the oxidation half cell reaction. That's already taken into account with the negative sign that is listed here. So when we are finding the cell potential, we have the reduction potential for the cathode minus the reduction potential for the anode. The minus says that we are taking the anode's reduction potential and turning it into an oxidation potential, is what's going on. Okay, went through a bunch of equations. The most important of these are the relationship between equilibrium constant, standard Gibbs free energy, and standard cell potential. This triangle is in the text. And then the Nernst equation, which allows you to determine the cell potential under non-standard conditions as defined by the reaction quotient Q. So that's the very, very brief touching on what it was we talked about on Monday/Tuesday. The next things we're going to look at are essentially a series of examples that we're going to go through. The first several are going to be primarily focused on galvanic cells. So this is an example of one of the first types of commercial batteries that was available. We have the electrical contact on a metal cap at the top. We have a metal bottom cover at the bottom. So we have the positive charge here, the negative charge here. We have a carbon rod electrode that is sitting inside a paste made up of some of the reactants that we're talking about: manganese oxide, ammonium chloride, zinc chloride, and water. We have a porous separator. The porous separator here is acting as the salt bridge that we are using. And then we have the zinc, a zinc coating on the inside of the can that is holding the battery together, and that is acting as the negative electrode. And we see here what's happening is that the zinc is giving up 2 electrons to become Zn2+, which now diffuses in and becomes part of the this paste that is in here. And then the opposite reaction that's happening is, let's see, it is turning the manganese from its oxidation state here of +4 into an oxidation state of, I believe that's going to be +3 in this case. And so the electron transfer that happens goes from here to here. So that's a standard kind of arrangement for a battery. A more modern version of a battery is known as an alkaline battery because it's happening under basic conditions. Alkaline means basic. We have a similar kind of arrangement of the electrode covers that we have. In this case, the bottom cover is electrically connected to a spike that comes into the center. We have 2 regions of sort of pasty powder, manganese oxide with coal dust acting as the cathode on this side, and in here we have zinc powder with potassium hydroxide. And so we have a similar reaction before the manganese is doing the same thing that we saw in the previous one. The zinc, instead of just becoming zinc 2+ and coming into the center, is becoming a zinc oxide material instead of the zinc chloride material that we were seeing before. Even getting more modern here would be a nickel cadmium battery. And the geometry of this one is pretty interesting. So we have a separator here, which a porous separator, and then we have a non-porous coating here that essentially blocks that blocks transmission of anything. Actually, that's not that. Yeah, I think that's how that works. But notice when we look in here, we've got 2 different shades of kind of blues and purples that we're dealing with. So the light blues are in contact with the top, and the purples are not. Down at the bottom, the purples are in contact down here, and the blues are not. And so that is how we end up getting all of the purple ones attached to the bottom to serve as the negative electrode, and all the blue ones are attached to the top to serve as the positive electrode. Why do we do this? because we have a huge amount of surface area now along this entire rolled structure to allow to be the salt bridge, to allow various to allow the ions to diffuse along. If we look back at these kinds of examples, if we have the diffusion of ions, they have a long way to go before they can get to the salt bridge. In this kind of arrangement, they have much shorter distance to go, and so that improves the performance of the battery quite significantly. Okay, so those are just some examples of commercial batteries and how those work. Let's now take a look at a concentration cell. And ignore this thing up at the top. That's something I added yesterday as I was working through an example problem that we might end up doing a similar one of today. So a concentration cell is a cell where the oxidation reaction and the reduction reaction are very explicitly opposites of each other. So if you imagine writing down the standard cell potential for this, where you look up what's the reduction potential for nickel 2 going to nickel neutral, and you look up the anode reaction, nickel going to nickel 2, the anode reaction is the negative of the cathode reaction, and so it should have a standard cell potential of 0. But remember that a standard cell potential is what you have when all of the concentrations are 1 molar. In this case, what we're doing is we're setting it up so that one of the concentrations is less than 1 molar by quite a bit. And so as a result, we end up having we have a modified cell potential using the Nernst equation, and we find that this reaction happens on this side so that we are giving up electrons, making more of the Ni2+. Electrons flow over here to take some Ni2+ from the solution and deposit it onto the cathode, resulting in solid nickel. And that procedure happens until we get to a point of having equal concentrations on the two sides. And so there's a voltage that shows up here when the concentrations are not equal, and you can calculate that potential, that voltage using the Nernst equation. As the concentrations move towards equilibration, that voltage drops until it reaches 0 when the concentrations are in fact equal. That's the idea of a concentration cell. Okay, a fuel cell. So one of the problems with batteries of any kind is that you end up using up your reactant, and you end up saturating the system with your reaction products, and the voltage drops at that point, and you end up having no more power coming out. Well, what would it be like if you were feeding reactants into your system continuously, and you were pulling out of the reaction continuously the reaction products? It's still an electrochemical reaction that's happening. You still have an anode and a cathode, but the result of this process would be that concentrations or pressures aren't changing over the course of the process, and so you can maintain a constant voltage. You can maintain a constant electrical power that you're outputting in this regard. So that's the idea of a fuel cell. So you have an electrochemical cell, you feed in reactants on the two sides, and on at least one of the two sides, you have products that you're pulling out. So let's look at how this particular example works. In this case, we have hydrogen gas coming in. It is dissolving into the anode material here, and electrons are getting pulled off of it, leaving you with H+ ions. The electrons cross over here and add to oxygen molecules that come across to the point that they split into O2- ions, which diffuse over here, join with the H+, and you now have water, which you can then pull out as a waste product. And so you generate electrical power as this happens, and we have a continuous feedstock that we introduce. We introduce the hydrogen on one side, the oxygen on the other. Now notice that this reaction here is the combustion reaction for H2, but it is happening in a non-combustion kind of way. It's happening in an electrochemical cell, so we are capturing the energy not as heat and gas pressure and all of these sorts of things that can happen in a combustion reaction. We are capturing it as electrical power. These kinds of systems tend to be significantly more efficient in terms of the amount of power you get out for the amount of energy that you put in than do internal combustion engines. And so there has been for a while quite a bit of a push to try to get fuel cells into automobiles. The problem with that is that you would need to have ways to have a compressed tank of hydrogen and a compressed tank of oxygen. And imagine what's going to happen at that point if you have an auto accident. You now have a recipe for an explosion. Now, this might be able to work just on air, 20%, so you may not need to have the full pure oxygen and as a compressed gas. And you can use things that aren't compressed gases. You could probably use methanol, for example, as a fuel source over on this side. And so people have certainly talked about doing these kinds of things, but it has not really taken off as much as many people would have hoped. And there are a variety of reasons for that. But the idea of using an electrochemical fuel cell, because it is much more efficient than a combustion engine, is certainly a very appealing one for future technology development. Okay. I also briefly mentioned that, that corrosion is a galvanic process. So what we have going on here is that the oxygen molecules are coming in here, and they are acting as the cathode, so they are receiving electrons to become O minuses down, and they're getting hydrogens, they're getting electrons from the iron that is getting etched away on this side, and you get forming water on this side. And then the iron 2+ that is formed, dissolving away from the iron material that you have here, is combining with more oxygen to form rust, a deposit of rust onto the surface of the material you're looking at. And so because the dissolution of the iron 2+ and the combining with O2 to form the rust happen at different locations in this deposition process, you end up getting this pitting and then a growth of rust on it. And this is why rusting or corrosion of iron tends to be so destructive. This is in contrast to how aluminum, for example, acts. When you have aluminum reacting with oxygen in the air, then it forms a uniform thin layer of aluminum oxide on the surface. And so that once that aluminum oxide layer has formed, then it no longer the air no longer has access to the unmodified aluminum inside, and so it's protected by the surface. That kind of protection on the surface is called passivation. But you are passivating the surface when you coat it, when it self-coats, or you deliberately coat it in a way that it prevents the access of atmospheric oxygen or other corrosive components to reach the metal that you're trying to protect. You can certainly fight corrosion by painting your surface. But the problem with a painted surface is very simply that the paint can wear off over time. You can also fight corrosion by making alloys. So stainless steel has a small amount of chromium that is mixed in with the iron. And the chromium collects at the surface and makes a thin oxide layer of chromium oxide, which does form a uniform surface in the same way that aluminum oxide does. And so that ends up passivating the surface of stainless steel. You can galvanize it by coating your iron with a thin coating of zinc. We do that by an electrochemical method called electrolysis, which we will get to in a couple of slides. The idea here is that the zinc itself has a lower reduction potential than iron, and so when there's a choice of which one is it going to reduce, the zinc oxidizes first, or which is going to be oxidized. I'm sorry. So the zinc is going to oxidize first, and so the iron is left untouched as a result. And a final example of a way you can use concepts of electrochemistry to protect an iron object is to use a sacrificial anode. So if you've got an iron tank that's underwater, maybe this is something that's used like as a septic tank or something of that sort, then you can make a sacrificial anode, which is made of some other material that oxidizes before iron does. So zinc would be a good example of that. You have it in close enough proximity to your object that you can have ion transport to complete the circuit across here. And then you run a wire, a lead wire over to, I don't know why, a lead wire, that's not actually lead, excuse me, a lead wire that goes over and connects to the sacrificial anode, so that when there are excess electrons here that, when there's electrochemistry going on due to the presence of moisture, the presence of oxygen, anything of that sort, then the sacrificial anode starts to etch away before the object you're trying to protect does. Now, it's sacrificial in a very important sense. It is going to actually eat away. And so once this thing completely eats away, it will no longer be protected, and your object will end up starting to corrode at that point. All right. Finally, we want to talk about electrolysis. So in a galvanic cell, which is essentially everything we've talked about up until this point, even a concentration cell and and corrosion are all, and a fuel cell. Those are all different types of galvanic cells. In those cases, you write down your redox reaction and you figure out which way it is going to be spontaneous. And then the electrochemical cell operates in that direction, in the direction of spontaneity of the reaction. Well, so when you do that, you have a certain voltage that the electrochemical cell will be producing as a result of that. Now, imagine taking a battery that has a higher voltage than that voltage that is being supplied by this circuit. And you then put that into the connecting circuit backwards, so that it's applying a larger voltage backwards than the cell itself can apply forwards. What happens in that case is that the electrons are forced to move in the opposite direction. And you've now taken a reaction that was formerly non-spontaneous, the reverse of a spontaneous reaction, and you have made it spontaneous by forcing it to go that direction. And so as a result of that, you can then do a variety of useful things with that reaction running the other way. For example, if you take chlorine gas and sodium metal and combine them, they will very violently and very, and with the release of a lot of energy, they will form sodium chloride, that's table salt. Definitely not the most efficient way to make table salt. But this happens so violently and so with so much energy released because the elemental forms, Cl2 gas and pure sodium metal, are at very high energies. And so trying to find chlorine gas or sodium metal in their native states in an environmental system, you just can't do it. They are not, they will have reacted away to something. But for a variety of industrial applications, we need both. We need pure sodium metal and we need pure chlorine gas. So we hook up an electrochemical cell, we melt sodium chloride, which takes a lot of temperature to do that, and we have an anode and a cathode, and we apply a voltage source that forces the electrons to move against the direction of the reaction that would normally happen. And as a result of that, we start to get chlorine gas that bubbles out of this molten salt that can be collected, and we start to get pure sodium metal that starts to come out on this side, and we can collect them. So this is I think there are more efficient ways than this to make chlorine gas. I'm fairly certain there aren't more efficient ways to get sodium metal. An example that I think you may have done in the 112 lab is the electrolysis of water. So we're doing exactly the same thing we just described, where we have an anode and a cathode, and we apply a voltage source across it. And we have our water in a tank, and we can collect separately the gas that comes off of the anode and the gas that comes off of the cathode. Off of the anode, the oxygen comes, off of the cathode, the hydrogen comes. And we have this water mixed with some sulfuric acid basically to act as an electrolyte so that there's enough electrical conductivity to complete the circuit through this system. And this is also the idea behind part of the group activity number 5 that you guys have been working on. The final example of electrolysis I'm going to mention is electroplating, where what you are doing is forcing a reaction backwards, where you then have a metal that's in solution, and you are forcing the metal to deposit onto a cathode into a thin film on the surface of it. So you may have seen silver-coated or gold-coated jewelry or silverware or something like this, and that's exactly how this happens. You have an electrode that's attached, you have a sacrificial anode, you apply a voltage source pointed in the right direction, and you then force silver to go into solution, and you force silver that's in solution to deposit as silver neutral onto the surface. You can coat most metals this way. You can coat you can coat with copper, you can coat with tin, you can coat with zinc, which we mentioned earlier is galvanizing. You can coat with gold. It's easy to get a thin coating of just about any metal, as long as there is at least some salt of it that you can have in solution. That's electroplating. Finally, within that context, for electrolytic cells, either for trying to make some compounder element like the sodium we talked about earlier, or in terms of electroplating onto a surface, we can do stoichiometry on the reactions to determine how much silver you will deposit onto your surface, or how much sodium you will get. And so the connection between the two is Q, which is the total charge that is going to be deposited. So remember that Faraday's constant is the amount of charge in coulombs that a mole of electrons have. So then if you look at the redox reaction, and you see how many electrons are necessary to perform the reaction you're looking for, you multiply that by Faraday's constant to determine the number of the charge that you are ending up using. So, for example, in the silver case, where it's going from silver plus to silver neutral, you are using 1 electron per step. Once you know the number of electrons you're dealing with, then you can figure out how many silver atoms you are depositing. How do you determine that from the electronics of what's going on? Well, you measure the current, and current is just coulombs per second. So you multiply it by how many seconds you run the experiment, take the current times the number of seconds, and that tells you what your total charge is. You divide that by Faraday's constant to find out how many electrons how many moles of electrons you used, and then you use the stoichiometry of number of electrons to the reaction that you're performing to find out how much of the reaction you performed. Okay, so that is all of the new content. Are there any questions on any of this material before I go on to the muddiest points that have been posted? I'm going to move ahead a little bit into those new points, but if somebody types in a question over the material we just did, I will be happy to go back to it and cover those questions. All right, so there were a lot of questions that I handled yesterday on the group activity, You see here 3, 5, 6, 7, 9, 16, 17, 18, and 22. So if you have questions on those specific questions, then I recommend looking at the video from yesterday's. There were several questions we went into on redox and electrochemistry as well, that we got through those yesterday. And we did almost all of the ones we had on entropy and spontaneity. There were a couple more I wanted to get to, and then there are some new ones that we have on the group activity, and some new ones on the electrochemistry and redox stuff. So one of the questions that we hadn't gotten to, so any of these you see up here, we handled yesterday. The arrows where we're starting for today. So confusing entropy and enthalpy, is there a good way to remember which is which? So this one I was actually just going to throw open to people in the chat. Does anybody have a good mnemonic or something to identify which entropy has to do with the disorder of the system, and enthalpy has to do with the heat transfers? The way that I kind of remember it is that if it's about heat, there's an H, and only one of these two has an H, so that's enthalpy. Whereas entropy without it is has to be the other one, meaning that has to do with disorder. But if somebody else has a better mnemonic to use, please share it with us in the chat. Okay, somebody asked a question, how is spontaneity calculated? And then does it relate to activation energy or orientation? So no, it does not have to do with activation energy or orientation. So activation energy and orientation have to do with the kinetics of the system. And so that's the activation barrier you get over in order for a reaction to happen. Spontaneity, it has nothing to do with the activation barrier. It does have something to do with the relative height on an energy diagram of the reactants and the products, but it doesn't have to do with the barrier that is in between them. So the way to calculate spontaneity is very simply, you need to find the delta G for the reaction. And if it's negative, it's spontaneous. If it's not negative, it's not spontaneous. And if it's zero, it's at equilibrium because it's spontaneous both directions. That's really all there is to it. To calculate spontaneity, you calculate delta G. Okay, a couple more questions on the group activity. So I will call up a copy of the group activity. Let's come over here. Let's see. Google Drive. Okay, so I've got a copy of it right here. Let's go in. So questions, there's the general questions 2 and 4, and apparently the explanation from yesterday didn't make a lot of sense. So let's take a look. So question 1 is to write the chemical reaction for the electrolysis of liquid water. So you are told up here that electrolysis is splitting water into its component elements, hydrogen and oxygen gas. So you write water on the left as a liquid. You write the elements, the hydrogen gas and oxygen gas on the right-hand side, and you balance the equation. That's it for question 1. Question 2 is determining the standard enthalpy change for that reaction. Means calculate delta H standard. Delta H with a little 0 degree sign on it, which means under concentrations equal 1 molar and pressures equal 1 bar conditions. So you, in Appendix G, you have the enthalpies of formation, and we remember that the enthalpies of formation, the formation reactions have the arrows pointed away from the convenient intermediates to the compounds, and so it ends up being enthalpies of formation of the products minus enthalpies of formation of the reactants. That's all there is to it. So Kendall says, is it possible I can do number 2? Sure, we can do that. So in order to do it, and Shane has correctly identified what the reaction is. So let us put Shane's answer in here. Oops, insert's what I want. Insert an equation. So 2H, actually, how do I do this? So H H2O liquid, we'd like an arrow, goes to H2 gas plus O2 gas. All right. So we will insert another equation here. So the delta H standard for any reaction, we are going to that H for the reaction standard is going to equal the delta H, let me do it this way, H of formation of the products minus the delta, here I'm going to just copy, H of, too many deltas, the delta H of formation of the reactants. This is because if we have, insert, little box here. All right. If we have reactants, let's make our font bigger. And we have our products. And we have our convenient intermediates, which in this case, because we're using formation reactions, are the elements in standard state. So I'll abbreviate that elements in standard state. Then as we put our arrows in place here to show us what's going on, we're going from reactants to products is our main reaction. Elements in standard state to reactants is the formation reaction. Formation produces the compound from the elements in standard state, and from elements in standard state to products. So if we are going to use Hess's law to get from reactants to products via an alternate pathway, we go here, which is against the arrow, meaning that we have a negative sign in front of the delta HF of reactants. We go with the arrow here, which means that we have a positive sign for the delta H formation of the products. So now what we do is we just put in the numbers. So what our products are H2 and O2. Now, we don't even need to look these up. H2 is hydrogen in its standard state. So its delta H of formation is 0, because the reaction we would be writing here is H2 goes to H2. There's no, the delta H is 0 for that. O2 is the same thing. So the only thing we need to worry about here is this one, which is going to be the delta H of formation of the reactants. So we need minus the delta H of formation of the reactants. So I give you a link to this. Let's open the link, I'll bring it over here. We need water liquid. So we scroll down to H2O liquid. And so the first column was delta H of formation. So we have negative 2, because there are 2 moles of H2O liquid on that side, times negative 285.83 kilojoules per mole. That's it. You now multiply that through, and you get a positive 500 something. That's all this question is asking for. The next question here was question 4. How do we do that? Well, you do exactly the same thing that you did here, just using instead the entropies. Now, in this case, the entropies are not entropies of formation, they are absolute entropies. So what does that mean? What it means is that the delta S of reaction is going to equal, stop it. S298, we should have, I'm going to actually do this differently. Nope, here, there. S298, of the products minus that same thing for the reactants. Now, this isn't, for this case, we don't have to go through this whole thing, because we are not talking about a delta S for a reaction. We are talking about the absolute entropies that we have. And in this case, what we remember is that for any change, the change of something means the final state of it minus the initial state of it. So the if we look at our change in altitude, and I climb a mountain, then it's going to be the altitude at the top of the mountain minus the altitude at the bottom of the mountain. It would be kind of silly to say I climbed a mountain and my change in altitude was -1 mile. No, it's +1 mile because I went up. So you take the final state minus the initial state. The reason we can't do that up here is because we're not talking about the absolute enthalpy of the system. We're talking about the enthalpy for a reaction, and we have to think about what that reaction is. And so here, you just look up the numbers again, and you do it just like you did here. Now, because we are talking about the entropies, the absolute entropies of the system, you cannot do the same thing we did here, where we just said, well, H2 is going to be 0 and O2 are going to be 0 because they're already elements in standard state. This has nothing to do with elements in standard state. And if we look at our appendix over here, we see that aluminum solid has a delta H of formation of 0 because it is, this is referenced to the element in standard state, and this is the element in standard state. But its entropy is actually a number because this is the actual absolute entropy. All right, I've probably beaten that point into the ground a bit much. So, all right, so here we go. The question, why is the sign what it is? So a lot of people had trouble interpreting question 5. I talked about this a little bit yesterday. Why does your answer to question 4 have the sign that it does, and give at least 2 contributing reasons? So when you do this calculation, you're either going to find that it's positive or that it's negative. That's what I'm talking about by the sign that it has. Whichever sign you come up with, why is the sign what it is? Now, the person who posted this question said, well, it's endothermic. So that's why it has the sign that it is. Well, this is about entropy, not about enthalpy. So no, this has nothing to do with endothermic or exothermic down here, not at all. Instead, what you look at is the reaction that you have here. What do we have, and we're comparing the reactants to the products, and what do we expect to happen in terms of entropy as part of this? Shane correctly identified that one of the answers to this is states or phases. We are going from liquids to gases, and the entropy of gases is larger than the entropy of liquids. So that's one of the 2 explanations. Does anybody have an idea of what the second explanation could be? Number of things, 1 reactant to 2 products. Well, that's on the right track, but more specifically, I would say that you have 2 reactants going to 3 products. You have 2 molecules on the left for 3 molecules on the right. And so as a result, you end up having more ways to arrange 3 things in space than you do 2 things in space. Or for a given amount of energy that you have, that energy can be distributed amongst the 3 things on the right in more ways than they can be distributed amongst the 2 things on the left. So yes, so the change of state is 1, and the change in number of molecules is the second explanation for what's going on for 5. And so that tells you that your answer to question 4 had better be positive because the entropy goes up for both of those two reasons. Okay. So let's see here. So in question, I'm a little confused about this, asking about question 5 and 10. 10. Maybe let's just talk about question 10 since we just talked about 5. Using the data in Appendix G, what is the standard enthalpy change for the reaction you wrote in question 9? And the question here is, do we mean standard 1 mole or specific to the reaction? So I think that's misunderstanding what is meant by standard enthalpy change. Standard means under standard conditions. That means that the standard enthalpy change means that it's happening at 295 degrees C, Kelvin, or 25 degrees C, and it's happening where pressures are at 1 bar and where concentrations are at 1 molar. So, and we designate that with a little superscripted degree sign that is next to the delta H or the delta S or the delta G or whatever we're talking about. So it has nothing to do with anything like a standard 1 mole. When it says the standard enthalpy change for this reaction, it is for this reaction as written. Okay, now this is not the correct reaction here. This is an example I did to illustrate how you determine what the combustion reaction for something is. So don't get confused about why methane has suddenly shown up here. I just decided to do a different combustion reaction than the combustion of hydrogen to illustrate the concepts. Okay. And I think that was it on the group activity muddiest points that were not also addressed yesterday. So feel free to throw more questions at me in the chat. When those come up, I will do something about them, but I'm going to move on to some other muddiest points until such questions show up. Okay. There are some redox questions, so I think we don't need this anymore. So I'm going to, what am I going to do? I'm going to bring up a new Mathematica notebook here so that I can type in formulas and things pretty easily. So that can go away. We'll do that, and I'm going to make this bigger. Okay, so we have a half reaction, 2Cr3 plus aqueous goes to Cr2O7 2 minus aqueous. And the question is, how many electrons are needed to be added to make this work? Well, it's tempting to look at this and just say, well, all we need to do is look at the charge. But we have to remember that we need to use the half reaction balancing method in order to do this, because we also have these oxygens that need to be dealt with. So if that's what we start with, the next step that we do is we make sure that we have the same number of atoms of the thing that's changing oxidation state on both sides, which we do. And so then the next thing we do is we balance the number of oxygens by adding waters where necessary. There are 7 oxygens on the right, so we add 7 H2Os on the left. Oops, that should not have gone in front of the aqueous symbol. There. Now we have the next step is that we balance the hydrogens by adding H pluses. We have 14 hydrogens on the left, so we need 14 H pluses on the right. Now we balance the charge. So on the left, we currently have 2 times 3 or 6, a plus 6 on the left. On the right, we have a negative 2 and a plus 14 for a total of plus 12 on the right, which means that we would need to add 6 electrons to the right to bring that down to a plus 6. So the final balanced half reaction would be plus 6 electrons. And so the answer to that question is that the number of electrons that's added are 6. All right. There was a Newton question. on which form of R is typically used in the Nernst equation. So I'm going to come back up here and find the Nernst equation, which I think was here. Right, so this is the Nernst equation. And honestly, the answer I'm going to give, which I don't think Newton would like, but I don't care. The answer that I'm going to give is you use the value of R that will cancel the units. That's it. So if you've got temperature here, you've got Faraday's constant, which is coulombs per second. You have N here, which is in moles. And so then R needs to be in something that's going to end up canceling to give you volts. That's all there is to it. And so what is a volt? Well, we had that up here. A volt is a joule per coulomb. So that would make sense that what the version of the equation that you use should be the, what is it, joules per mole Kelvin, something like that? Joules moles per Kelvin second. No, that's not it. I don't remember what it is. What are the units for R? Gas constant. So joules per Kelvin mole, yeah. So if we take this, so I'm just gonna type that, put that somewhere else so that we can play with it. I'm just gonna put things in here. If this is going to be joules per mole Kelvin, if the temperature is going to be in Kelvin, if N is going to be in moles, and if F is going to be in coulombs per second, is that, no, that's not coulombs per second, it's coulombs per mole, I think. Now there's an interesting little thing about this one, about the units of M that we have here. So let me write this a little better. So this is, what did we say? This is joules, no, this is coulombs per mole. So the units on N in this case are actually somewhat unusual. They are moles of electrons over moles of the reaction as written. So you put, if the reaction you wrote exchanges 2 electrons, then it's 2 moles of electrons per 1 mole of the reaction as written. And so this mole cancels with this. This mole cancels with this. We go through and we find that the units end up being joules per coulomb, which is a volt. So I don't like the idea of Newton saying, always remember to use this form of R, because these are things that it is worthwhile as a check to yourself to make sure that the units cancel right, to go through and ensure that you can get the units to cancel. That way you can avoid most of the mistakes you'll make in calculations in chemistry. I would guess that 90% of mistakes come down to not tracking units well. All right. Continuing on. So I think that was it on those. And so then I had some sort of randomish questions about earlier stuff. One question was, diamonds are considered kinetically unstable. Why? They are not considered kinetically unstable. They are considered kinetically stable. They are thermodynamically unstable because it is spontaneous for diamonds to convert to graphite. But the activation barrier to that conversion is so high that it never happens over the lifetime of the entire universe. So no, diamonds are not considered kinetically unstable. They are considered kinetically stable because they are thermodynamically unstable, but the kinetics prevent them from decomposing. When calculating KSP, how do you know the ratios in the equation and how does it relate to a balanced chemical equation? So a KSP is just an equilibrium constant. There is nothing more to it than that. So write down any ionic compound. So something like this. Well, its dissolution reaction is that going to 2Al3 plus 3SO4 2 minus, like so. And so when you write down the equilibrium constant for that reaction, you put products over reactants. So it's Al 3 plus squared, because there are two of them, times SO4 2 minus cubed, because there are three of them. And in the denominator, you would put this if it were aqueous, but it's a dissolution reaction, so it doesn't go in there at all. So that is your equilibrium constant. So there is nothing special about this being SP rather than just any old equilibrium constant. You form this the same way you do any equilibrium constant. What is the common ion effect? The common ion effect is when you have a series of reactions that have an ion in common between them. So an example of this would be using one salt to precipitate part of another salt. So if you have silver nitrate in solution, what that means is that you have Ag plus in solution plus NO3 minus in solution. If you have sodium chloride in solution, you have, oh, this isn't actually a common ion effect. I'm doing this different. I'm doing this wrong. Let's actually write this as an equilibrium, and let us suppose that we then also have AgCl aqueous that we have already dissolved into water. So we have Ag plus aqueous, and we have Cl minus aqueous. Now, this equilibrium that we have, is pretty far shifted to the left because silver chloride is not very soluble. I think that's right. But if you add some silver nitrate to the system, then that silver nitrate is going to increase the silver concentration in this reaction as well. And so you're going to end up getting more precipitate of silver chloride because of the common ion effect from the silver that you have added. The idea of this is that when you have multiple things going on and they affect one another, what you do is you trace the reaction, the Le Chatelier's principle, to see how one of these changes affects something else. So if you have the silver going up, then this reaction is going to shift to the left, and you'll end up getting more product, and the chloride ion concentration will go down as a result. How can a salt act as a buffer, and how does its solubility affect it? So a buffer is very specifically a case where you have an acid type, and its conjugate base in equilibrium with each other, and you have close to the same amount of the acid and its conjugate. So you will typically form this by taking HA at some concentration and then taking something like NaA minus, NaA, sodium A, and making an equimolar solution of these two kinds of things. So that's how you make a buffer. There's not a lot else to it than that idea right there. How does its solubility affect it? Well, one issue with solubility is if you're making a buffer with a combination where one of them is not particularly soluble, then you may not have a very high buffer capacity. So it may buffer it, but not against a huge amount of added acid or base. How do you determine the pKa of a titration where there are multiple equivalence points? Okay, so it is probably a good idea to look at a titration of polyprotic acid. So let's look at one of these. And so what we will do is take image address. Okay, so we have here the titration of a biprotic acid, and so you find your first equivalence point, and you can find that on this axis very precisely because it's moving very sharply at this point. So you can find that it took 8 milliliters to get there. So half of that is 4 milliliters, and so at 4 milliliters you find out what the pH was at that point, and you can find that very precisely because you know 4 precisely, and so you can find that level very easily. You then come over here, find the pH of it, and that pH is the pKa for the first deprotonation step. If you look at the second deprotonation step, you find its equivalence point here at 16, which you'll notice is twice the 8 that you had. Halfway in between those, so at 12 milliliters added, is going to be the second midpoint. And so you can find that very precisely. You look over at the pH, and that is the pKa for the second deprotonation step. That's all there is to it. Okay, there's a question, or it's a comment in the chat. Salts give the equilibrium the capacity to shift in both directions as a result of adding additional acid or base. I think that any buffer has that capacity because if you are using, I mean, whatever you've got here, if you are at a point where HA equals A minus or is very close, then the Henderson-Hasselbalch equation works in both directions on that. So I don't know that that's something special about a salt. I think what I would need to know is what kind of salt is it that they're talking about. There may be some specific type they mean. Maybe it's a type that has a weak acid, an anion that acts as a weak base and a cation that acts as a weak acid. And if both of them are buffering simultaneously, maybe something's going on with that. I don't know, but I would have to know what they mean by a salt in order to be able to figure that out. Okay, and I've gone through all the muddiest points that I have here. So we have about 10 or 11 more minutes. Please feel free to speak up if anybody has a question. I have taken off the prohibition against unmuting, so if you want to just speak and tell me what a question is, I'm happy to try to address it. Or if you want to type it in the chat, that's fine too. Oh, mute button's locked? Oh, I changed it the wrong way. My bad. I apologize.
So I was just wondering on when you were doing the half reaction balancing, is the reason you left the water charge out is because it's neutral?
Where did we do that?
It's in the Wolfram. It's
Was that in this part here? So you're asking why that's not included in the charge?
Yes.
Yeah, it's neutral. So each one has a charge of 0.
Okay, that's what I was just wondering.
Okay.
So I kind of had a question on that same thing. Doing the half reaction, we know that we start with a 6 positive, and so we add the last step was adding the 6 electrons, so that basically we end up with the same net charge in the system of positive 6.
Yes. So that if we were at a position before we added those of having a +6 on the left-hand side, and on the right-hand side we had a -2. Nope, nope, I'm sorry. So because I got rid of that. So before adding those electrons, that's where we were. And so we had a +6 on the
Can't
left.
see what you're doing.
And then on the right, we had a +12. And the only thing we can do at this point is add electrons. So if we add electrons to this side, we make it worse. If we add electrons to this side, this charge starts to come down, and we need 6 of them to bring it down to the +6 that we have on the other side so that it's balanced. Does that make sense?
Right. I can't see what you're doing.
Oh, I'm not sharing screen. There we go. Thank you. Okay. Yeah, please speak up when I do something stupid like that. Okay, so before we added the electrons, this is the what we had. And we had a +6 on the left-hand side, and we had a +12 on the right-hand side. At that point, the only thing left to do is add electrons. And if we add electrons on this side, we're going to make things worse because we're going to make them further apart from each other. If we add electrons to this side, for each electron we add, the total charge goes down by 1. So adding 6 electrons to this side makes both halves of the reaction have a +6 charge.
Right. I was just making sure that that's what we're trying to do. We're not trying to make one neutral versus the other.
Right.
It's trying to match the start to the finish.
Yes, that's correct. Because you do have to remember that this is still a half reaction. And so the other half reaction will then be taking those 6 electrons and having them on the reactant side.
Got it.
One thing I did yesterday was I came up to the concentration cell example, and I went through how to use the Nernst equation to actually calculate what the voltage is. Is that something that you guys would be interested in seeing as well?
Absolutely.
Okay, so the idea here is that if you were to write the full reaction, so I'm going to bring up, why doesn't that work? If you're going to write the full reaction, if you're not careful, everything is just going to cancel out. So okay, and then so if we took both of the 2 half reactions and added them together, we would get something that looks like this. And it's tempting to say, okay, everything's the same on both sides, so we just cancel them. Except that when we are dealing with a concentration cell, the concentration of this on this side is different from the concentration of this on the other side. So this part cancels, the electrons cancel, because those get transferred across the salt bridge. No, across the wire. The solids don't factor into Q, the reaction quotient, so we can get rid of those. But we have to leave the anode aqueous concentration of nickel 2+ and the cathode aqueous concentration of Ni2+. And so when we write the reaction quotient for this, it's going to be this concentration at the anode divided by this concentration at the cathode. And so when we plug that into the Nernst equation, which we have here, E cell standard is 0 because that's where everything has 1 molar concentration. And so whatever E anode is, it's going to be the same as E cathode, and they're going to just subtract off. But you do then have this term here where Q takes into account that you have a different concentration in the anode than you do in the cathode. And that is what produces the cell voltage that you then see.
In this particular reaction, would N be 2? Because you're getting 2 moles of electrons for every mole of reactants.
Wonderful question. Let me go back and check. Yes, absolutely. It would N would be 2 in that case. And the weird unit thing I was talking about, that is 2 moles of electrons per mole of reaction as written. So it's formally unitless because it's moles over moles. So in terms of preparing for the midterm number 4, I really want to draw your attention to this, this diagram here that shows the way that you connect a cell voltage to a standard cell voltage to a standard Gibbs free energy and to an equilibrium constant. So this kind of idea here becomes this central set of relationships that connects all of the types of manipulations that we've done in the last 2 weeks, which is what's going to be on the on this midterm. You know, all the concepts of free energy and all the concepts of redox and equilibria. And so what would make sense to expect would be to have a system that is probably going to be a redox system that could probably be put into an electrochemical cell kind of situation. And then you can go through and calculate things like what will the cell potential be? What will the standard cell potential be? But then you also have the balanced redox equation. So you can then calculate the delta G standard by using delta H's and delta S's from standard thermodynamics tables. And so then those would be 2 different ways, independent ways that you could then get the equilibrium constant. And so trying to do that both ways and then comparing them, are they the same? Are they different? Are they the same within what makes sense for them to be the same? You know, that's the kind of things that you could kind of expect to see drawing together many of these concepts. And it looks like we are at time. If anybody has any last questions or comments, I would be happy to hear them. Otherwise, I have a test to finish writing.
So going from delta G to K,
Uh-huh.
assuming you don't know K, obviously, or is that kind of one of the things that we would have to solve? And in doing that, you would figure out delta G divided by negative or even positive RT, and then raise that to 10 to the negative to solve for K?
No, it would be e to the, because that's a natural log. So you're going to have e to the negative delta G standard over RT. Yes. Where that whole thing is raised to the power. That's how you go from a calculated delta G using tabulated thermodynamic values. That's how you use that to find the equilibrium constant. Yes.
Okay. I think that's
all right.
Totally enough to confuse me forever. But are you going to post something as far as office hours availability during next week?
Yes,
Are you gonna
yes,
have
I
any
will.
availability?
I don't know what that's going to be looking like just yet because I am still panicked about trying to get the exam finished and written. I need to make sure I get that into your hands. So,
okay.
Expect that I will have something posted probably tonight with some more details about what my office hours are going to be.
Certainly. Thank you.
All right. Thank you. Bye-bye.